Our final presentation today is going to be from a man who is also going to do some show and tell for us today. So please give a warm round of applause to Mr. Marc Raibert.
Thank you.
Have fun.
I love building robots, and it's great to be here with all of you to talk about it. I'm going to start out by doing a demonstration of really, truly remarkable sensory motor control. Okay, here goes. Thank you. It looks so easy, but there's so much going on for me to stay balanced on my feet. Here, I'll up the ante a little bit. I'll walk, or I'll even run. And when I do that, my brain, my sensors, my muscles, my body all work together in order to provide that. And all we're trying to do when we build robots is to get those skills and perceptions and mechanical designs into machines, into robots. I think our long-term goal is to do this, to build robots that have the functional levels of performance that are equal to or greater than people and animals. I don't mean that they have to work the way people and animals work or that they have to look like them, just at the level of performance in terms of mobility, the ability to move around in the world, dexterity, the ability to use our hands. Look, I'm handling this device, I can rotate it around, I'm sensing. There's a remarkable amount going on that we make seem so easy. And then perception. I mean, here's a room with 200 people just within this theater, and I can look and see every one of you. I can do it while I'm moving. It's totally remarkable, yet we can all do it and we don't think about it. We didn't have to be specially trained. Yet those are the skills that we're trying to put into our robots. As a company, Boston Dynamics is trying to do two things now. We're trying to look to the future to develop the skills and sensing and controls that are going to make a very high level of performance possible, as was in the previous slide. So we're trying to shoot over the horizon to make the future happen. And at the same time, we're trying to take what we already know and reduce it to practice by making robot products. So the robot products is new for Boston Dynamics. We've been operating for a long time, working on the future, on the advanced stuff, and now we're trying to make some practical products, which I'll talk about up here on the stage. So here's a little chart that shows the idea of having two goals. The blue circle is lower capability. One axis I have is mobility, and one is manipulation. There's also cost, reliability, safety. There's modest goals for them, which I would call products that we're going to have this year, next year, and the next few years. And then there's more advanced capabilities that we can't do yet, that we're working on. And as those become available, much more useful and advanced and even money-making applications will be possible, and we're working towards that as well. So what are some applications that we can do today? Here are some of those. We think we could make robots that are used for entertainment. Just judging, we were taking one of our robots and walking it around the show floor here, and at least for geeky type viewers like all of you, people want to look, they want to take pictures, they want to interact with the robot. So I think there's a good case for making robots that are entertaining and making a business out of that. There's also commercial security. You know, I don't know how many security guards are. There's about 1.5 million in the United States who just go and patrol a site to make sure that everything's happening as it should and to report any problems. And it's pretty clear that we are already doing testing with some of our robots for that kind of application. And then emergency response. For instance, I visited the Fukushima nuclear reactor site in Japan that was damaged by the earthquake, and they still have people in protective clothing cleaning up the environment there, and clearly robots could be used for an application like that. I think two other applications that are right available in front of us in just a few years are warehouse logistics. There's already some robots being used there, but there's many other things that can be done, and we're working on some of them. And how about parcel delivery? In the United States, Amazon sends packages, and other companies are sending packages to everybody's house on a very routine basis. And right now, that involves someone driving a car and delivering. And I think that many of those tasks could at least be expedited, if not be automated, by using robotics. But here are some of the longer range, more important solutions. I think the one in the upper right, the idea that we'll use robots to help take care of the disabled and the elderly, is really important. In the United States, something like 31 million people spend a large fraction of their time taking care, about half of their time, taking care of disabled people, either their family or other people. And that can be really a burden that I believe eventually in the future robots will help alleviate. And I think those are good things to use robots for. If I look at the robots we've built at Boston Dynamics, I would roughly assess their capabilities in these areas. The one in the lower left is an older robot, and the ones to the right are the new ones we're building. So here's that older robot, Big Dog, that we've been developed about 10 years ago. And the main goal was to make a robot that could travel in the world, the unconstrained, undefined world around us. And part of our approach is to use dynamic balance and controls. And that's why this robot can balance itself even when it's disturbed and when it slips on ice. And the robots that followed can be used in all sorts of terrain. Here, the robot is following a human. There's no driver. So it uses its vision system and some other sensors to track where a human is, and then it goes right along behind them, dealing with obstacles. Why do we make robots with legs? This is terrain that no wheeled vehicle can travel on. And that's the fastest legged robot in the world. Mostly an enjoyable experiment. I don't know, we haven't continued to work on the cheetah, but it was certainly interesting to see if we could reproduce some of the dynamic behavior and controls that are found in that robot. So these are the 4 robots we're working on today, and I'll give you a little status report, an update on them and what they're doing. And I'm going to start with the Spot robot. Spot is a 4-legged robot, smaller than Big Dog, electrically powered. And it has truly remarkable terrain mobility, much more mobility and autonomy than the Big Dog robot that preceded it. And that's because we learned a few things about how to design the hardware and software that made it much more feasible for use. So we've been experimenting with the idea of delivering packages to people's homes. These are our employees' homes, so we're not just going out to the random public. That's one of my partner's wives. So this is a little bit contrived. But the idea is that we're experimenting with the various terrain and situations. And in the Boston area, which is where we're from, there's many different kinds of stairways and door entries and things like that. And we're doing about 75 to 80% success on the kinds of places where our employees live. Part of that success is based on a very vigorous testing program that we do with our robots to make sure that the control algorithms can really handle the terrain and the disturbances that the real world has to offer. I think this kind of testing is the most important thing I can convey to you about what we do, because it means that the robot can work in a wide variety of circumstances, not just in the situation that was planned in advance. Here we've put an arm on the robot, and so we're doing mobile mobility. And again, we're testing in a way that means the robot has to determine that it's not succeeding at what it's doing, make up a new plan for it, keep its balance and control while that's happening, and not get derailed by the situation. We believe that having the ability to respond to the local environment like that means that robots will be much more successful when they're connected to higher level AI, because the higher level AI can worry about the big problems that it has to solve, and the low level AI, like we build, will deal with all the variations in the local terrain. The next robot is Spot Mini, which is the first robot that we, Boston Dynamics, are commercializing. And we have a Spot Mini here. And Ben Swilling is operating it. It's using its sensors to see the terrain. And it's using onboard computers for its gait. You may not know it, but Spot Mini was greeting you just there. So I'm going to give a demo in a couple of minutes, but before that, I'm going to tell you a little bit more about the robot. So Spot Mini will be back. We designed this robot to be small enough so that it could fit inside of an office or a factory or warehouse, or even someday a home, even though home use isn't where we're starting. It's also light enough. It weighs about 27 kilos, 60 pounds. It's light enough so that a human can be near it, and at least if you're, many humans are not afraid to be near it because it's not big like our previous robots. It has cameras on it, which I'll show you in a couple of minutes, and it's designed as a platform. So here's some video of Spot Mini operating. There's the old Spot standing up, and Spot Mini can walk through it. Earlier we were on the show floor, and someone got in the way of it by standing like this, and Spot Mini went through its legs. And this isn't a real home, and those aren't real people, those are engineers. This is a mock-up of a home that we use to do testing of the robot to show that it can handle different kinds of stairways and fit in tight spaces. A thing we've learned is that making a robot behave in a very confined space is much harder than making it work out in the woods, because in the woods there's usually a lot of room. It doesn't matter exactly where you go. Here we're showing that the robot can look for footholds and make a planning operation where it adjusts how the body moves and how the feet move to adjust to the environment. Same here. This is not pre-planned. Someone's just telling it to go forward, and the robot is seeing the obstacles and avoiding them. There's a dynamic obstacle. And when you put all the reflexes, controls, and perception together, you can get a robot that works in the unstructured world as well. Now, this is an ordinary chicken, but it does remarkable things. It can keep its head stabilized while its body moves. And we gave Spot Mini the ability to stabilize its hand when its body moves, and it's pretty much what people do. I can hold my hand here and move my body all around it. And that means that the control can think about what the hand's doing, and all the rest of the coordination happens automatically. Here's another demonstration where the software, there's no human involved here. It's using a camera in the hand to find the door handle. It's been told to go through the door. And it's using coordination between the hand, the arm, and the body in order to negotiate. And in this case, it's a good Samaritan letting the other robot get through the door. Now, we're not being mean to the robot. The robot has no feelings. It's not angry at us when we do this. And in fact, we're like proud parents showing that the robot can succeed even though it keeps trying and we keep giving it a very hard time. But we believe that testing like this is the key to making robots that are going to work in the real world and that are going to work well when they're connected to higher level AI processes. Now, the Spot Mini robot is designed as a platform. That means that we've designed a mobility platform with all the sensors and controls needed to make a robot that can travel around the world. but it has facilities for attaching additional hardware and additional software to customize it for particular applications. So this robot arm is added for tasks where we need to handle things. There's a computer and radio in that white box that are added. Boston Dynamics built these, but we plan for third parties to design payloads, we call them, that are added to the robot to specialize it for different customers' applications. And you can imagine applications like the one I've mentioned: security, delivery, construction. We're already doing testing in several of those areas with potential customers. And this robot will be available starting next year. We've built 10 by hand. We're building 100 with manufacturers at the end of this year. And in the middle of 2019, we're going to begin production at the rate of about 1,000 a year. So I mentioned that this is a platform that can have applications. Here's an example of an application where we've written, or an application group has written what we call a patrol route. And it has been driven through this space earlier, and now it can autonomously navigate this space. In the lower left, you can see the data previously collected, and superimposed is the mapping or the perception of where the robot is on the map. And it's just traveling where it was supposed to go. If there's an unexpected obstacle, it can detect that and go around it. You can see that in the lower left here, it's showing you what the perception system sees, and it can see the obstacles it's facing. When it came up the steps here, it was using data just like this, so it can adjust the footsteps and adjust the body. One of the quirks of a quadruped like this is they frequently have trouble going downstairs because of the shape of the legs. So we have Spot Mini go downstairs backwards, and it's just like going upstairs forwards. And it turns out there are many dogs that don't like going down steep stairs as well. Anyway, this is a completely autonomous run, implemented outside the robot, but in the onboard payload computer. And it's just one example. Here's another example of an application that we wrote outboard. This is like a magic act where it's 3-can Monty. And the robot has a sensor in its hand, and it's going to pick up the can and move it to another space. And we're externally coordinating the robots. And here's a case where we have 4 robots. And really, it's up to all of you to think of the application where you could get a basic Spot Mini and either work with us or with others to build hardware and software that runs on it that solves your application. So I'd like to do a robot demo now, and Ben Swilling is helping me. For this demo, all the motion of the robot is done autonomously with the computers on board, but he is steering the robot and giving it high-level guidance. And again, when we do some of these apps, it's more automated than that. So here Ben is just going to demonstrate basic locomotion. Here it's walking with a crawling gait, or animal people would call this a crawl. Now it's switched to a faster walk, where one leg's being picked up at a time. This is a trotting gait. Now Ben doesn't have to do any of the coordination. All that's done by the computers on board. I think he's going to switch to a pace, which is, in a horse, a pace would be the legs on the left and the legs on the right. Usually only animals with long legs do that kind of walking. Now, one of the cool things about a legged robot like this is it's omnidirectional. So why don't you come over to here to do it can walk sideways. In addition to frontwards and backwards, it can walk sideways. It can turn in place. And it can pose the body. So let me say something, and it can go up and down. Let me say something about posing the body. I'm going to change the conversation to manipulation. There are many robot arms in the world, mostly doing manufacturing tasks, but most of them have their shoulders fixed in space. So the place they can reach is limited by the joints on the arm And it's also limited by how big the hand is, the workspace. And most robot arms really have a very small volume they can work with. But by having an arm on a mobile base, it has a huge workspace. Even without moving its feet, the robot can reach from down on the, this is a small arm. It can reach up to here. It can reach as in the space that Ben's showing. And Ben is controlling this by telling the hand how to move, and the body is just following along. And of course, if the robot walks around, it makes the workspace be the whole room. Now, I showed you the chicken before, so we're going to show you chicken head mode. And this is where the hand is stabilized while the body moves. And it's not perfectly stable. It's jittering a little bit, but it's pretty good. Okay, how about pitching and pitching and... So this means that we can do tasks where the hand does things in the world and the coordination with the body can happen automatically. This robot has, this robot has sensors. There's 2 pairs of cameras in the front. And why don't you turn around a little bit? Can you pirouette? And there's another camera here. Go ahead, one more. And there's another camera in the back and one on this side. So it's looking at the world all around it. And one of the things it uses those cameras for is to adjust its feet when it comes up steps or goes over an obstacle like that one. You notice it picks up the feet to step on the obstacle, and it pitches the body a little bit. This is a pretty simple obstacle, but it's convenient for doing on a stage like this. The robot also has some, okay. I'm feeling a little thirsty. Spot, can you get me a soda? So Spot has a camera in its hand. Ben drives it so it's close to the thing, but then it searches with that camera and grabs it. In this case, Ben's driving it, but it could have it automated. Thank you, Spot. Finally, I told you before that Spot is a dynamic robot, and that means it has some gates where it can put energy into kinetic energy and elastic energy. So can you do a little trotting? And Spot Mini is a little bit of a show-off. It loves to up the ante. Now, I think our engineers should do a gate where it goes just on one leg, but we haven't gotten that going yet. Thank you, Spot. Thank you, Ben. I'm going to talk about a couple of other robots we're working on, but after the show, we'll have the robot out here. And if some of you want to drive it, you can come up and get another demo and take it out for a spin. I just want to say a couple of words about the humanoid robot, Atlas, that we've been working on. But to set that up, I wanted to talk about a principle of robotics that I don't think everybody's caught on to. I think a lot of people think that this is the architecture of how a computer-controlled robot works, that there's a robot, and it's got some sensors, and there's a computer, and the data from the robot is sent to the computer, and the computer thinks about things and tells the actuators on the robot what to do. And I think this is true, but it's not the whole picture. The whole picture is that the robot is really interacting with a physical world where gravity, friction, moment of inertia, potential energy, and kinetic energy are all forces that tell the robot what to do, in addition to what the computer tells the robot what to do. And really, to be successful in robotics, for advanced robots, you want to design the hardware to acknowledge this fact of life, and you want to design the software. And we think of this as an organic design where all these pieces are designed and conceptualized to work together. And I don't have time today to go into exactly how we do that, but I think there's a lot of progress in robotics that has been made and will be made by taking the physical machine into account. Now, one of the elements of building hardware that's suitable for this world is to make it more like people and animals. So this over here on the left is a standard robot leg. In fact, that was a leg from the Big Dog robot. And it uses separate components for actuators, hydraulic lines, connectors, sensors, and valves, and many other components. And having all those separate components means the design is kind of big and very heavy and not ideal. And the thing in the middle is a concept drawing of what it would look like if it were an animal-like robot leg. And we've been working very hard using 3D printing techniques to build the humanoid robot using more 3D printing and more animal-like parts. And here's a picture of some of those pieces. And that upper center piece is a leg, the equivalent of what I showed in the previous slide, where all the components are printed into the design. Not all of them, but many of them. And it means that the leg weighs about 1/3 of what the previous leg weighed. It has the same strength and a bigger range of motion, all because we were able to shrink things down. There's some other components on the left. One of the most interesting ones is the center in there. That's the power supply for Atlas. And it weighs 5 kilograms, and it puts out about 5 kilowatts of power. That is a very high density. And we achieved that by integrating a motor, a pump, a reservoir, an accumulator, filters, and all the connectivity, a heating jacket. And many of those components are printed into a design that has everything together. Now, I have to warn you, doing it this way is very labor-intensive still. You need a lot of engineering design. It's very expensive, and in some cases, it's slow. But I believe as these things mature, this will be the future over-the-horizon thinking of how to design and build complex systems like robots. Using this approach, we started with a humanoid on the right that weighed about 375 pounds. I don't know what that is in kilograms. It must be 170 kilos or 160 kilos. And we've been able to shrink it down, and both that Atlas robot and I weigh about 165 pounds. I think that robot's got a few pounds on me, but we're about that. And that makes it much more useful design. So here is the Atlas robot out in the world doing a few things. We always try and test it in a realistic environment. Here it's walking, it's using its visual sensor to determine the stairway, very much like Spot Mini does. In this case, there's also a laser rangefinder where Spot Mini uses all cameras. Here we're taking advantage of the fact that the arms aren't stable on a base, but they're attached to a mobile base, so the upper body and the legs and the arms can all work together to do this manipulation task. If you were to do this with a traditional robot, you'd need a giant robot that weighed probably 1,500 pounds, maybe 700 or 800 kilos to do the same task. And here we're starting to work on getting the robot to work at speeds that are about like human speeds of doing tasks. Not a very friendly working situation yet, but we're working on that. And just as I said before, we love to test the robot. Here the robot's been told to pick up this box. It's using a visual system. In this case, it's using the QR codes in order to be able to see where the box is. It picks it up, and then our guy is being the proud parent and showing off the capability. It's not being angry. Now, I happen to think that dynamic behavior is really an enabler for robots, and so we've been working on making the robot travel faster using dynamics, incorporating the feedback and the energetics, the understanding of the energetics as I described before. And we've been using that to do some new things as well. This is on YouTube, so I'm sure many of you have seen this before. We're working on getting a version of this that we can take to shows, but we're not quite there yet. Thank you. Now a lot of people look at our robots and somehow get psychologically connected to them and ask us about what emotions the robots have and what are they feeling. Are they angry? Are they upset? And if you look at our YouTube site, you'll see lots of people commenting that the robots are going to get back at us and all that. Well, the truth is we don't give our robots any emotions ourselves. But fortunately, the YouTube community has taken up that job. And so I just have 2 videos to show, not made by us. It's our visuals, but their soundtrack. And if the audio people can turn up the sound a little bit.
I love you, Box. Good night, Box.
This robot's really in love with his work.
I love you, Box. Good night, Box. Box.
But the make.
Time to make the f***ing donuts.
But this guy isn't so happy.
All right. Gosh, you got a boot or something. Okay. All right.
Anyway, you get the idea. If you look at it on YouTube, there's a bunch of others. Thank you all for listening. Ben and I will hang around for a while if you want to come up after and play with the robots or talk to us. Thank you.